this video, we're going to explain the basic steps to derive Einstein's general relativity field equations from one principle, the thrifty universe principle. That's crazy. Okay, so this is the generic equation by Einstein for general relativity. Actually, it's a simplified version, but that's enough for what we need here. The full detailed derivations that we are trying to achieve here would probably take a couple of days. So we will not go through a full derivation here, but I will at least explain the major steps to derive these equations from the TUP, the thrifty universe principle. Now, let's think for a moment about what we're trying to achieve here. We were trying to find in the mathematical world the isomorphic equivalence of what happens when gravity makes things move in the physical world. In our case here, in 4D spacetime. It sounds a bit complicated. So let's first look at what happens in classical physics. In the classical physics world, in 3D space, there are several ways to express the laws of motion, which means to describe in the mathematical world the movements that we can measure in the physical world. One of them is Newton's way, another one is the Lagrange way, a third one is the Hamilton way. Well, it turns out that my favorite one is the Lagrange way. Why? Well, because we can directly derive it from the TUP, of course. So I'll give you a quick reminder here, but if you want to know more details about the thrifty universe principle, the principle of least action or whatever, well, you're going to have to watch my previous videos. Now, in mathematical terms, saying that the action of the actual trajectory is optimized is the same as saying that its variation is equal to 0. So we need to apply that in a 4D space-time volume, since space and time are linked as soon as you talk about relativity, Therefore, in that case, the action looks like something like this, Now, in classical physics, we've seen that the Lagrangian here is a function of, dx over dt and x, also, which measure the position of the particle object and its derivative. And that was assuming one-dimension movement, like on a line. Now, in the case of space-time, this is a Lagrangian density. And what allows to measure space-time is a special tensor called the metric tensor. Again, we've seen that in previous videos. So we're looking to find a Lagrangian that is a scalar function of the metric tensor and of its derivatives. Just like the classical Lagrangian is a function of x and of its derivatives, dx, dy, dz. This Lagrangian scalar turns out to be the Ricci scalar. So we could try the action being equal to this, here, where the Lagrangian would be the Ricci scalar. But the problem is that we want to make sure that the action will be invariant when we change coordinates. And both Einstein and Hilbert came up with the solution, it's called, not surprisingly, the Einstein-Hilbert action, defined by this here, where G here is the determinant of the metric tensor, You can find in the literature or in the internet a derivation for this. And again, we don't want to derive everything in this video. But the idea here is that the 4D volumes stay invariant when you change the system of coordinates. And the square root of the determinant here corresponds to the volume form, whose integral over pieces of space computes volumes as measured by the metric G. Not that until now we didn't assume any matter energy in the considered spacetime. Okay, but we'll take that into account in the coming slides. So let's go back to our main question. How does the TUP allow to derive Einstein equations for gravitation? Well, the TUP tells us that the Einstein-Hilbert action variation should be equal to 0, So that will be the hypothesis, the basic assumption we'll start from to derive the Einstein field equations. So let's go for it. The first step will be to calculate the variation of the Einstein-Hilbert action and see what happens when we set it to 0, which is what we do here. We can first replace the Ricci scalar here with its value from the Ricci tensor, which can be defined using the tensor rules that we've seen before. And therefore, we obtain, this. Okay, piece of cake for now. So we have seen that on every point in the space-time manifold, there is a Riemann tensor, which basically tells you how space-time is curved, by looking at how fast parallel geodesics will change and become not parallel. So in flat space, they stay parallel, but in a very curved space, they will rapidly move towards or away from each other, And that's the basic principle of how a Riemann tensor is defined. It's expressed like this, which is not looking very easy. But again, here, the idea is to decompose it into more fundamental symbols, like these gamma symbols here, which are defined there. And there are arrays of numbers, called Christoffel symbols, and they depend on the metric tensor. However, they are not tensors. But the good news is that you can use tensor notations to represent them, and therefore you can use them, and that will simplify the tensor equations. So that's what we'll do. And when you do that, and you develop the integrand here, then you apply some boring and tedious calculus of variations rules on the Riemann and Ricci tensors, and eventually you get something like this, And by the way, since we want that the variation is equal to 0 for any metric we use, that will imply that this is equal to 0, which is the case when there is no mass energy, in other words, in a flat spacetime. So from this and from the Riemann and Ricci tensors, we eventually get something like that. And of course, I'll give you some links if you want to look into that a little bit further. And since the variation can also be written as this, we can easily derive from this and this that this particular value here is equal to that. Okay, so let's keep that. And now look at what would happen if we add mass or energy, to our space here. Well, then the total action, will become something like this. The action that we've just seen here, plus the action due to the mass, or the mass energy. So the new equation, with mass and energy becomes something like that. The total action here, the action that we saw before, and the action due to mass. And so you replace, this that we just calculated here with its value, and then we keep that like this. Okay, so now we can still apply to the total action the TUP rule, for it. And that will become this, which means that. Okay, it's very basic. Let's keep that last equation here and have a look at it. Well, first of all, we can see that there is a tensor here, because there's a tensor here which happens to be the metric tensor. But wait, this actually not only look like a tensor, but actually it's I know, there is this energy momentum tensor called T mu nu, which is equal to that. And, we're not far from that here. And this tensor here, T mu nu, happens to reflect all the mass, energy, densities, and flows in a given space-time volume. How lucky we are. Wow, fantastic. And knowing that K, given the correct units, is equal to this, we finally get from all of that this equation here. This equation, I'm sure you've noticed, is the Einstein field equation, or equations if you consider that tensor equations are in fact multiple equations. So now that we saw that these equations could be derived from the thrifty universe principle, the TUP, let's see what they actually mean, because that was also the purpose of this video. Well, they mean that if the energy momentum tensor here is not zero, which means there's mass energy, the space-time geometry here is changed. It's curved, which is why we feel gravity as a force, because our body structure, like any other body structure actually, is bent, due to this presence of matter energy. And all of this can be explained using the TUP, because the universe wants to compensate any change due to potential energies around us and do that in an optimized way. And again, this is a TUP rule. Isn't that fantastic? Yeah, that's amazing.